This is a review of Chapter 6 from Geosystems Core, and we're going to be talking about global climate systems. The topics that we will cover will be components of Earth's climate system, climate classification system, and we will consider tropical climates, mesothermal climates, microthermal climates, polar and highland, and dry climates. So here are some big picture questions and concepts. I want you to think about how are climates classified, what differentiates climates of tropical and mid-latitude regions, what differentiates climates of microthermal and cold regions, and what differentiates climates of dry regions. And so I want you to know the main characteristics of each of these types of regions, and I want you to be able to describe how climates are classified. So we'll start out by considering weather versus climate. So weather can be considered the conditions at any given moment. It's reported in days, sometimes 3, 7, or 10-day forecasts. And climate is a pattern that emerges over time. And so climate is long-term and includes the conditions of an area for a year, whereas weather would typically be short-term and reported on a much smaller time scale. The study of climate is climatology, and it analyzes long-term weather patterns over space and time and the controls that produce Earth's diverse climatic conditions. So there are broad similarities that exist in climates, and they're grouped into climatic regions. So there's two main components that interact to produce what we know of as climate, and that's precipitation patterns and temperature patterns. So remember that precipitation includes many different forms of water. So we have rain, snow, sleet, hail, snowflakes, mist, fog, dew, and this map is showing you the different types of classifications based on the number of inches of precipitation. And you can see patterns here that show the highest areas of precipitation occur along the equator in South America, Africa, and parts of Asia and India. And please notice that at the poles, there's actually the lowest amount of precipitation. So the driest areas on our planet are actually in the Arctic Circle and in the Antarctic Circle, the continent of Antarctica, and portions of Greenland, Europe, and North America. So there are many components that interact to produce what we know and experience as climate. There's a complex interrelationship between insolation or energy from the sun, Earth's energy balance, temperature, air masses, air pressure, atmospheric moisture, and precipitation. And so the combination of these in certain ways can lead to very diverse climate types. So there's many different factors that are all acting on the same area, and that's what's meant by an interrelationship. All of these physical phenomenon contribute to produce the climate of each area of the world that we classify. So you can see here an example of a very lush and green climate. So there's a lot of precipitation. There's running water through the middle of the scene, but you can tell by the amount of vegetation that there is a lot of available precipitation in this area, as opposed to this type of an area where it is very, very dry, and there's really not any precipitation, there's really not any vegetation that you can see. So there is evidence of precipitation, and those landforms were carved by both wind and water. And so there is precipitation in this area, but there's not a good set of conditions for a lot of vegetation. The method that we're going to focus on is called the Köppen Climate Classification System, and these are the basic climate categories: tropical, mesothermal, microthermal, polar, highland, and dry. So tropical is warm and rainy year-round, and there are rainy seasons and dry seasons, or wet seasons and dry seasons. Mesothermal is the mid-latitudes. Meso, it means there's a mild winter, and meso actually means middle, and so it refers to the climates between extremes. Microthermal occurs in mid to high latitudes, and this is where we have cold winters. Polar areas are high latitudes and polar regions. They're cold year-round, and there's no true summer or what we would consider to be a warming up period. Highland would be high elevations that occur at all latitudes. So you can also consider this to be high altitude. And that means that in areas where there are large mountain ranges, you will have a highland classification, which is very similar to a polar classification, and sometimes those are grouped together. And then we have dry, which is a permanent moisture deficit at all latitudes. So for each climate category, a climograph can be produced. Climographs are the tools of climate classification, and they show temperature and precipitation for a certain weather system. So here's an example of a climograph for Madrid, Spain, and notice that the months of the year are represented by letters on the x-axis, and on the y-axis, if we look at the left side, we have precipitation in inches and centimeters, and that is represented by the blue bars in this graph. In the same graph, we also have temperature, and the units for that are found on the right side y-axis, and it is showing in degrees Celsius and degrees Fahrenheit. So this is an example of a climograph for Madrid, Spain. It's showing you the latitude and longitude of this location, which is 40 degrees and 28 minutes north, 3 degrees and 33 minutes east. And the labels on here are showing you the times of the year when there are cyclonic storm tracks, and then the subtropical high occurs during June, July, and August. So we talked before about interrelationship, and so this is showing you 6 main factors that are all included in this interrelationship. So starting with number 1, we have insolation, and as we've learned in a previous chapter, incoming solar radiation is the energy input for the climate system. Insolation varies by latitude, and there is an excess of energy at the equator, and there is a deficit of energy at the poles. Insolation changes with day length and sun angle or time of year. And then number 2 is that energy-earth balance that I just touched upon a little bit. There is an imbalance that's created by energy surpluses. So we have more energy at the equator, and we have less energy at the North Poles. There is a circulation pattern of winds and ocean currents that moves this excess energy from the equators to the poles, and this helps regulate our planet so that we don't have the extremes that we would have without these circulation patterns. If you look at number 3, the primary temperature controls on an area are latitude, elevation, the amount of cloud cover, and the land-water heating differences. So temperatures remain more stable and don't have as much variation or fluctuation near the coast, whereas inland areas that do not have strong coastal influences will have a wider range of temperatures. And this pattern of world temperatures is affected by global winds, ocean currents, and air masses. Moving on to number 4, air pressure is also going to affect the climate of an area. So winds in general flow from areas of high pressure to areas of low pressure. The equatorial low creates a belt of wet climates. Subtropical highs create areas of dry climates. Pressure patterns will influence atmospheric circulation and the movement of air masses. And then finally, oceanic circulation and multi-year oscillations or changes in pressure and temperature over the oceans also affect weather and climate. Number 5, we have air masses. So this is showing you a warm front, which is meeting a cold front, and the warm front is being pushed up where the warm air is lifted abruptly. And when we talk about homogeneous means the similar conditions, and that's referring to the cold air and the warm air. Vast bodies of homogeneous air form over oceanic and continental regions, taking on the characteristics of their source region. As these air masses move or migrate, they carry their temperature and moisture conditions to new regions. And then finally is a pattern of atmospheric moisture and precipitation, which we considered in Chapter 5. And this is known as the hydrological or water cycle, where we have cloud formation, precipitation, evaporation, transportation, and surface runoff. Here is an example of the Köppen climate classification system. And so you can see the main areas of the tropical, dry, mesothermal, microthermal, and polar climates represented by the different colored polygons. This map is also showing you air masses, which we have studied in a previous chapter, and those abbreviations: M for maritime, C for continental, T for tropical, and P for polar, and there's also E for equatorial, A for Arctic. Tropical climates are the most extensive on Earth. They 36% of the land and ocean areas fall under a tropical climate, and there's a consistent day length and insolation and steadily warm temperatures. The effects of the intertropical convergence zone bring rain and shift seasonally with the high sun, and the warm ocean temperatures and unstable maritime air masses are characteristic of this area. So here are the tropical climates of the world represented with different shades of green. The tropical rainforest climate is consistently warm and moist. The ITCZ is constant, and it's characterized by enormous water surpluses. So here is a representative climograph for a tropical region of Uapes, Brazil, and you can see that there are very large blue bars representing precipitation over all months of the year. In fact, the lowest month is September, and there is 15 centimeters or about 6 inches of rain per month in that lowest month. And then if you look at that climograph, you can see that May and December are above 12 inches of rain per year. The temperature doesn't vary much at all. It stays very, very consistent, and that purple line is almost a straight line. So there's really not much seasonality. And the picture here is showing you a rainforest along the Rio Negro River in Brazil. So the ITCZ is responsible for the precipitation pattern throughout the year. In a tropical monsoon climate, there is a dry season that lasts 1 month or more when the ITCZ is not overhead, because the ITCZ is a zone and it shifts. So for about 6 to 11 months out of the year, rain falls in a tropical monsoon climate. Here is a representative image and climograph for Hanoi, Vietnam. You can see that between May and September, there is quite a bit of precipitation. The temperature doesn't vary very much, and so that purple line does have a little bit higher values in the summer months of June, July, and August, and there's a little bit cooler, but again, this is not very extreme seasonality. In tropical savanna climates, they are located poleward of the tropical rainforest climates, so both north of the tropical rainforest in the northern hemisphere and south of the tropical rainforest in the southern hemisphere. The ITCZ reaches roughly 6 months out of the year as it migrates, and the summers are wetter than the winters. So you can see that there's a dry period here that is represented by June to October. And this would be a typical climograph for Arusha in Tanzania. And it has a characteristic landscape with plants that are adapted to seasonally dry water budgets. And you can see that those types of tall trees would have root systems that would take advantage of the wet months, with April being the highest recording of precipitation. And then if we look at our temperature, again, not much variation. Moving on to mesothermal climates. 40% of the world's population lives in this type of climate. There is an increasing variability of day length, which means that in the northern hemisphere, we have longer hours of daylight in the summer, shorter hours of daylight in the winter. And there is also an increase in the variability of the amount of insolation moving poleward or towards the poles from the tropics. The summers transition from hot to warm to cool. There's a shifting maritime and continental air mass, and this is guided by upper westerly winds. There's variable precipitation from low and high pressure systems, and this brings changing weather conditions. There are variable sea surface temperatures. These impact air mass strength. It is cooler along the west coast of all of the continents, and it's warmer along the east coast. Here are the representative areas of mesothermal climates shown in blue and brown shades. With humid subtropical climates, they're characterized by having moist all year, or they can have a distinct winter dry period. The summer is warm with unstable weather, and the air masses interact in other seasons, and the different types of mesothermal climates are humid subtropical winter dry and humid subtropical hot summer. So here is a representative climograph for Chengdu in China, showing Asian monsoon effects. And so there's 10 times as much precipitation in the summer than in the winter. And now we're starting to see a little bit more variation in that purple line, which is our temperature, meaning that there's starting to be seasonality. And the shifting ITCZ and subtropical high determine the precipitation pattern. Here is an example of agriculture fields in an area that does get quite a lot of precipitation. Another type of mesothermal climate is the marine west coast climate, where there's mild winters and cool summers. They're characterized by cool, moist, and unstable maritime polar air, and that's what controls the climate. It's coming from the polar regions, and it travels southward, and so that's why things are pretty cool during the summer. And this is very characteristic of Europe and other middle to high latitude west coasts. So if you've ever been to San Francisco, it's a marine west coast climate. So here is an example of a climograph from Dunedin, New Zealand, and you can see that there is a steady amount of precipitation throughout the year, and there is a decrease in temperature in the summer months. So New Zealand is in the southern hemisphere. Their seasons are opposite of the northern hemisphere. And then a representative meadow, forest, and mountain on South Island in New Zealand is shown. In Mediterranean dry summer climates, at least 70% of the annual precipitation occurs during the winter months. This occurs on the western margins of North America, central Chile, southwestern tip of Africa, southern Australia, and the Mediterranean basin. This is primarily controlled by the shifting subtropical high pressure cells. Here's an example of San Francisco, California, a mesothermal climate where most precipitation is occurring in the winter, and there are dry summer months. These dry summer months are due to a subtropical high. In a microthermal climate, it's cool temperature to cold, and this represents 21% of the land surface on Earth. There are increasing differences in day length and seasonality, meaning that the number of hours of daylight changes during the year with more range than we saw in some of the other climates we've discussed. There are decreasing sun angles and highly variable day length. So the sun is not directly overhead in a lot of microthermal climates. We also get precipitation from cyclone air mass conflicts in the winter, and there are convectional thunderstorms in the summer. The continental polled air masses dominate winter, and they are very, very cold, coming directly down from the poles. And there's an Asian winter dry pattern associated with continental polar air masses. Here are the areas of the globe that have microthermal climates. So you can see that they're in relatively high latitudes if we think of our reference point as being the equator. Moving on to humid continental hot summer climates, there's a distribution of annual precipitation that's fairly even. There are maritime tropical air masses that influence both humid continental moist all year and humid continental winter dry climates in the summer. In this part of the world, you experience interaction of continental polar and maritime tropical in the winter, and this brings frequent weather activity. So here's a climograph for New York, New York, and there is a pretty consistent amount of precipitation throughout the year. There is warmer summer months and then cooler winter months. And this is referred to as summer convection because there are cyclonic storm tracks all year long. When we consider humid continental midsummer climates, the precipitation is less in the hot summer regions to the south, and there's heavier snowfall, and this helps with soil moisture. So here is a climograph for Moscow, Russia, and you can see a slight increase in the precipitation in June, July, and August, and that corresponds with warmer temperatures. This is due to continental air masses. In subarctic climates, they're located further poleward, and there's greater seasonal changes, and there's a very intense short growing season. So here is a representative subarctic climate, and this is Churchill in Manitoba, Canada. Most precipitation occurs as snowfall in the winter months, and then it is stored. It doesn't melt off because of the very cold temperatures. You'll notice that the temperature does increase during the summer, and it is very, very cold during the winters, below 0 degrees Celsius or 32 degrees Fahrenheit, which is below freezing for most of the year. In polar and highland climates, there's no true summer. There's a low sun altitude, and that's the main controlling climatic factor. There are extremes of day length between winter and summer, and they experience very low humidity. There is a decrease in surface albedo, an increase in surface albedo, which causes a decrease in the overall heat of the environment. So here's an example of a polar ice cap, and this is on the slopes of Denali. And this would be a very reflective surface, so a lot of sun's energy bounces right off of these tall mountain ranges and keeps the area very cool. In tundra climates, they are almost entirely in the northern hemisphere except for elevated regions in the southern hemisphere. They never go above 10 degrees Celsius. They're under snow cover most of the year, 8 to 10 months, depending upon the yearly conditions. And the ice cap climates can occur above tundra in elevated regions, even in the tropics. So you can have highland climates that have continual ice coverage in tropical regions if they are at a high enough altitude. So here's an example of a polar climate, and you can see it's obviously very cold by human standards. With ice cap and ice sheet climates, they cover Antarctica and Greenland. They're dominated by dry, frigid air masses where all of the months average below freezing. So here are the areas of the world where there are tundra and ice cap sheets. And you can see that Antarctica is a continual ice-covered continent. And so you can see here the relative size of some of these icebergs, ice caps, and ice features. In polar marine climates, they are more moderate than other polar climates. There's no month below -7 degrees Celsius, but they're still colder than tundra because of the marine influences. Here's an example of a polar climate for an area of South Georgia, Russia, and there is a fairly consistent amount of precipitation and not much variation in the temperature. So as opposed to the very early temperature graphs that we saw where the tropics were very consistent. This is also consistent, but you can see that it's consistently near freezing, which is 0 degrees Celsius or 32 degrees Fahrenheit. With dry climates, they are found in broad regions between 15 and 30 degrees north and south of the equator. A steppe is a vast semi-arid grassland. It's too dry to support forests, but there's too much precipitation for it to be classified as a desert, so they're called steppes. And they are characterized by a lot of grasses, not many tall shrubs or trees. There's a dry subsiding air in the high pressure systems, and there is location in mountain rain shadows where there's a lot of vegetation. Continental interiors away from moisture, and they're shifting subtropical high pressure systems. So I misspoke when I said that there's a lot of vegetation in the rain shadows. I should say that there's a lot of vegetation on the windward side of a mountain, and on the rain shadow side it's very dry. I apologize for that misstatement. Here are the dry climates of the world, and you can see in the red and the oranges representing arid desert climates and the orange steppe climates. So we have tropical, subtropical, and hot desert climates, where the average annual temperature is above 18 degrees Celsius. The rainfall does occur from convection in the summer, but it's very, very low amounts of rainfall, almost nothing. So here is a representative dry climate from Riyadh in Saudi Arabia. You can see that the average annual temperature never goes below 18 degrees Celsius, which would be approximately 65 to 66 degrees Fahrenheit. And you can see there's very, very low amounts of precipitation, and there is a representative sandy desert there, the Arabian Desert, in the image. This area is controlled by a subtropical high pressure. In mid-latitude cold desert climates, there's a small area, lower temperatures and moisture demand. There are tropical, subtropical, hot steppe climates. These exist around the edges of a hot desert. They're characterized by shifting subtropical high cells. This creates a distinct dry summer, wet winter pattern. The precipitation is still below 60 centimeters annual if it was added up and totaled. With mid-latitude cold steppe climates, they occur north of the 30 degrees latitude in the northern hemisphere, and they're not found in the southern hemisphere. The rainfall is highly variable and it's undependable. Here is a climograph for a dry area in Alberta, Canada, and you can see the rainfall is highly variable. So there's some months where there's appreciably more rainfall. So June has much more rainfall than December, and this area is controlled by a continental air mass of winter continental polar air. So these are some examples of conditions that occur because of climate controls. And so polar climate types are shrinking as Earth temperature rises. Moving over to the right in Eurasia, the Arctic tundra is shrinking. And there are changes in regional albedo as the trees darken the landscape and cause more sunlight to be absorbed. Dengue fever, shown in 6b, is one of several diseases that's spreading into new areas as climate changes occur. So the conditions are changing, and the mosquitoes are having more and more territory that is favorable to them. They tend to thrive in wet and very tropical areas with a lot of vegetation, and so the spread of mosquitoes is spreading disease among humans, such as dengue fever and also malaria. And then in the lower left-hand corner, as the tropics expand towards the poles, the storm systems are shifting towards mid-latitudes. The subtropics are becoming drier. We're getting droughts in some parts of the world and floods in other parts of the world. This is an example of a farmer looking at his cotton field, and normally the plants would be up to his knees, and you can see they're much smaller than that.